Hello conference chair, dear members and colleagues. I am Vikram Kumar Gupta, PhD scholar from IIT Kharagpur, India. I am going to present my research on the topic of tribological performance and wear-induced reliability assessment of laser powder bed fusion manufactured in Cornell Super 7-8 gears under the certain operating condition. So I am going to start with introduction. So additive manufacturing, also known as rapid prototyping, 3D printing and free-form 3D printing process that can deposit, combine and consolidate material as a metal powder to produce the physical objects layer by layer and with the help of the computer aided design. So the 3D printed parts are advantageous because of the low cost, lightweight and customized system and that create the complex and intricate geometries like a gear with the different materials like super high entropy alloys and etc. So it can also eliminate the need of a specialized tooling and machining process, reducing the material waste and the cycle time with the materials such as titanium, aluminum, and inconel. These are the figure shows below the different. So these are the gear made by the 3D printing process. This is the structure of the laser powder fusion process, and this is the defective gear produced by the 3D printed process. So we have to examine the different aspects of the 3D printed gear with in the lens of tribological performance and wear reliability assessment. So what are the motivation and research gaps? So explore the adoption and need for 3D printed gear with super alloys like in Cornell 718, especially for aerospace and jet industries and its useful cases. Real adoption need gear level evidence like in LPV of Cornell gears promise lightweight, fast build and complex geometry but lacks of gear per tribology and reliability data under the realistic variable duty cycle. Surface topography drives performance like what are the surface morphology, topography as built surface and what are the post surface topology after the post processing of the 3D printed gear leads to wear and different textures and orientation tied to the 3D printed gear. There are the different defects like residual stress, effect on the build orientation, post-processing technique like machining, short pinning, HIP, affect the fatigue, but there is no quantitative multi-scale linking process, property structures, and reliability map according to this. So this is important. So for the 3D printed gear, generally gear wear is not only reduce the transmission efficiency but may also lead to the vibration and noise, even gear failure in the severe cases. So we have to examine the what is the wear behavior of the 3D printed gears. So these are the methodology and testing session. Start from the material and geometrical selection. So we have selected the spur gear based on like some standard spur gears. So number of teeth is 20, 32 and 20 and pressure angle is 20 degree, module is 1.5. So small modulus gears for the precision applications and the inconel gear, the composition of the inconel is shown as here and so the different material property of inconel 718 powder. So we have like applied the sub process parameter to the 3D printing machine, laser powder bed fusion 3D printed machine. Like laser power we have selected 300 watt, scan speed 960 seconds, layer thickness 40 micron, hedge space 0.1 bed temperature 80 degrees Celsius and orientation angle is 0 degrees Celsius. So after getting the final gear from the 3D printed machines, we have checked some tribological performance based on the surface roughness. So as build surface and after some duty cycle, what is the surface roughness and the hardness value, the micro weaker hardness value of the as built surface with a different load condition and the pin and ball disc tribological meter, what are the coefficient of friction and wear rate behavior of the on this surface of the gear apart from the wear on this teeth. So after all these things we have applied to the gears for this multi real-time setup. So from this setup we have checked the wear on the tooth based on the arcade wear theory and degradation modeling. So what are the effect of the surface morphology on the wear reliability assessment of this gear? So these are the methods: microstructure, surface profile, and macro hardness analysis. So we have obtained the different setups like surface topography measured by the like Meteor to surface test, and metalographic sample with the CM ADS energy spectrometer, weaker micro hardness measurement performed by applying load of 1 kg of the duration of 10 seconds minimum 5 minute duration. So we have observed 3 indentation on particular point. So tribological performance analysis. So we have conducted the tribological performance like coefficient of friction and wear rate based on some different load 10 Newton, 30, 20 Newton, 30 Newton and frequency 5 Hz to 15 Hz with the different time scales and stroke length of 1 mm. And the reliability and wear performance. So we have, after the tribological performance assessment, we have applied the gear on the real time test setup, where we have applied the different test condition like the different RPM, torque, and test run. And after each run, we have measured the surface morphology as a surface roughness as a wear measurement, and we applied the damage and failure modeling shown in this formula, and with different operating condition as a viable distribution with alpha and beta parameters, and combined with the arcade wear models, and the finally stochastic degradation model per cycle. So after each run the degradation uh, then degradation happens, and like it have degraded like cumulative failures. So what are the surface roughness after the cumulative failures of the sediment area, and the reliability of that for a particular duty cycle with a different operating condition like RPM, load, and number of cycles. So result and discussion. So this is the inbuilt surface topology we have measured for the 2 mm area of the surface of this stretchy printed here. So we have observed the different peaks and constant peaks and different peaks of this surface on as built surface from the 3D printed machine. So this is the microstructure. So after the some finishing, so we got some microstructure from the G's microscopy, and this is the different rank of roughness number on the different part of the gear after the duty cycles. So this is the micro hardness values after the 3 integration at butt point at 300 gram force and 500 gram force. So we have got 420, 438, 425 at 300 gram force, and for 500 gram force we have got 505, 595 and 596. So now we average for 197 micro hardness values. So from this microstructure analysis we after some uh, etching and surface finishing, so we have observed that there is some porosity and columnar and grain structures, like you can see cellular area and columnar area, and there is a grain boundary with the different track length during the therapeutic track interface and porosity of somewhere. So and this is the resultant discussion from the tribological performance. That is coefficient of performance and VR rate. So from the coefficient of performance point of view, so there is a different value based on the 10 Newton, 20 Newton, 30 Newton values. So on average you got the maximum is coefficient of friction is 0.3456 at 5 Hertz at 30 Newton. So it's some increasing trend towards due to the load in due to increasing in load. And for 15 hertz there is a different coefficient of friction. At some point of time it converged at 30 Newton. This is some 2.0.2425 value. And for the specific wear rate, you can see from this figure. So the specific rate at coefficient of friction 0.024, this is 6 point 10 to power minus 6 millimeter cube per Newton meter. And like a specific wear rate for different 5 hertz, specific rate achieved is 10 into 10 to power minus 6 millimeter cube Newton meter. So these are the microstructure after the tribological assessment. So you can see the triboxide layer region sharing, leaving small cracks. So layer region due to the surface finishing and operation abrasive marks, and there is a sub detecting mark on particular from the microstructure analysis. So after this tribology assessment, we put the gear. So for examine the wear on the teeth specifically for the real operating condition with with lab setup at IIT Kharagpur. So we run the test setup at different torque and RPM and load. So you can see the different reliability and survival function curve with a different duty cycle. So at like uh, 0 4 at 4.5 Newton meter at 240 is a reliability achieves the maximum duty cycle is achieved is 60,000. So it is ranging between the 50,000 60,000 to the good life. Uh, so this also shows the reliability curve variable foot based on the surface roughness. So increasing surface roughness shows the decreasing the reliability curve of the gear wear of the teeth. So the conclusion. So from the examination of the corneal alloy sample involved in analyzing the microstructure, we saw the primary phase present in the alloy versus the uh, gamma phase. From the 3D profile, we revealed that specimen and the 30 Newton load at the cellist wear depth is 5.24 micrometer and the lowest surface roughness is 0.6 millimeter, indicating minimal wear with a smoother surface. So 9 intention, we already discussed the hardness value and the different scale. So from the load, we have examined the coefficient of friction of inconel 718. So it is constant at 715 hertz. Is got 0.24 value. So an unstable tribooxide film cracks and spells producing abrasive plugging. Evidence mixed oxidation abrasive wear mechanism of LPM inconel 718K. From the morphological state, dioxide layer played a crucial role in the changing the coefficient of friction value for the additive manufacture sample. In contrast, for M1 kernel 7 fibers, specific variety gradually climbed up 7.65 into 10 power minus 6 to 13.25 into 6, while at 1500 it is like 6 point into 10 to power minus 6 millimeter cube per meter. Wear mechanism from the gate is observe a tribooxide glaze that form under sliding, then cracks and spalls debris for abrasive plugging and delamination. So they are the different wear mechanism we got from the biological performance, and then from the test setup, real-time test setup, we plot the reliable survival fit. So the reliability declines sharply as the RA increases. Smoother teeth like between 1.2 to 1.15 retain 80 to 90% survival, whereas reference number is greater than 4 micrometer drives the reliability at 20%. So these are the different rank of the based on the operating condition and RPM values.